Something that one of my colleagues in the physics department mentioned, and I've really hooked onto the way he says it, is the output of our research labs is not grants, it's not papers, it's the students. What really matters most is what the students learn, how they develop skills, and where they go on to after they graduate. Optics is the physics of light. So just how light behaves, how it interacts with other things. I started getting into it when I was an undergraduate. I joined a lab that was called the Quantum Optics Lab, mostly because the name sounds really awesome. While I was working in the Quantum Optics Lab, what I noticed was the things that I tended to talk about most to other people were the things that had biological applications. And I think a lot of that was that it seemed more real. Something like, we are building a technology that's going to help people's lives now. And so I joined a lab that was working on medical devices and using optics to assess what was going on in cells and in tissues, and really figuring out how those cells and tissues behaved, how they were changing, how they were different in diseased versus healthy patients. And that was a lot more fulfilling to me, to both be able to look at the really cool effects that light has on things, but also be able to translate that into an immediate impact for real people. So in our lab at UVU, we do something called Raman spectroscopy, which is a technique that uses light to find out what molecules are present in a sample. The changes that we're mostly looking for in Raman spectroscopy are how the molecules either connect to each other or are shaped themselves. It's specifically looking at molecular vibrations. And so when a protein is in a different shape, it will vibrate differently. And this also applies to lipids, to DNA, to minerals found in rocks and in fossils. As long as there's a molecule, Raman spectroscopy is really good at detecting those changes in molecular composition and shape. A really neat project that we've been working on recently, I jokingly call it the world's most expensive meat thermometer. So we take some meat samples and heat them up, and heating them up changes the molecules inside. It actually makes the proteins change shape. And then when they cool back down, the proteins don't change shape again. And what makes that interesting for our application is we can cook our meat up to a certain temperature and cool it back down. And with Raman spectroscopy, we can see how the molecules changed, and we can figure out what temperature the meat had been cooked to before it got cooled down. The original idea behind this was we could look at burn wounds in victims and give this to a first responder. They could take it to the scene of a fire, wave their light wand over a victim, and see how burned the tissue was and make some decisions about that. Where we found some more ready applications are in the food processing industry. So whenever we buy some dino nuggies from the store, they're in the frozen section, but it says that they've already been cooked. But do we really know that they've been cooked? What our instrument could do is just measure those dino nuggies, see how the proteins have rearranged themselves through the cooking process, and we could actually tell what temperature the dino nuggies had been cooked to, even while they're still frozen. And that will tell you if they're safe to eat. And so a food processing company could potentially use this technology and put it as part of their assembly line just to double check that all of the dino nuggies have been cooked and are safe to eat before they go out to market. Raman spectroscopy can be applied to a lot of different things, whether that's geology or chemistry or biology or physics for physics' sake. But what really makes this a valuable skill set for students, it isn't Raman spectroscopy itself. It's being able to apply that basic scientific process of learning how a new technique works, learning how to use the device, and then identifying its strengths and weaknesses as you go along. Those skills sometimes get taught in classes, and we try to teach those foundational principles and how you learn those basic physics principles. But really those skills get learned most when you're actually getting your hands dirty in the lab and confronting those questions that don't have answers yet. And when students really get the chance to answer a question that nobody has ever answered, ever, then they get to learn how to approach those situations, and those skills go well beyond graduation into whatever they end up doing later.